So moving on, both the spring scales read force F using a free body diagram showing the forces acting on the block and their components. Derive an expression for F in terms of m, g, and theta. All right, so that derive, remember what that shows or what that means. It means show all of the steps to get an equation, that's what expression means, for F. So we're solving for F, and we need to have lowercase m, g, and theta in it, and nothing else except for constants. All right, so let's see. We have force at an angle, and that force is F. That force is F. Well, let's take a step back here. Let's not get too far. Let's not forget that if we're dealing with forces, the very first thing we need is a free body diagram. So let's go ahead and draw that. Free body diagram, there's our body, and we have the easy one, which is going to be our weight. And then we have a force in this direction called F, and we have a force in this direction called F. Okay. So using this free body diagram, we're now going to derive an expression, so show the steps to get to. All right, when we draw our triangle for this first F here, the red F, go ahead and keep this consistent all the way through. So when we're looking at this leftward force, we can resolve the components into the vertical components and the horizontal components. The vertical component, this part right here, this vertical line, is the adjacent side to the triangle. Meanwhile, the horizontal component is the opposite side of the triangle. And then, of course, we have our we have the hypotenuse, which is just F. So the magnitude of the hypotenuse is just F. All right, so when we resolve this into its x and y components, we have, in the x component, we've got opposite and hypotenuse. Opposite and hypotenuse is sine, so magnitude, trig, theta. And then we have, let's not get ahead of ourselves here. In the y direction, we have the adjacent and the hypotenuse. So that is going to be magnitude cosine theta. Okay, so we're getting there, making some headway. Let's move on to this second vector, this green one, this green F. Well, lucky for us, it's going to be the same triangle, just like this. So again, the vertical is adjacent and the horizontal is opposite. So we're going to do the stuff that makes it go minus the stuff that holds it back, right? That's always the next step after you draw your free body diagram. Step 1, identify it's a force problem. Step 2, draw a free body diagram. Step 3, Newton's second law, stuff that makes it go minus stuff that holds it back equals mass times acceleration. If we're in equilibrium, then there's no acceleration and it'll just equal 0. So horizontal, if we say the red is making it go, then the opposite would be the green, F sine theta. Equals 0 because it's not moving, right? So if we solve for this, we would just get F sine theta on one side equals F sine theta on the other side. It's not moving. It's not canceling out. It's kind of useless to us. For the y component, which I'm going to move all of this down. All right, so I've moved it all down here. We also have another vertical component, so it's going to be I'm sorry, the picture moved. So it's going to be F cosine theta for this green vector also, right? It's still going in the same direction. So we're going to say plus F cosine theta minus the stuff that holds it back. So if up is positive, then down must be negative. Well, what force is acting down? The weight force. minus mg. And it's suspended, it's not doing anything, so it all equals 0. Outstanding. But we're trying to solve for f. So now we get to do algebra from here, and we'll go ahead and solve for f. F cosine theta plus f cosine theta is going to be 2 times f cosine theta. I'm going to add mg to that side over there, equals mg. And we're going to divide by 2 cosine theta. Divide by 2 cosine theta, and we get, that goes away, that goes away, that goes away. F equals mg over 2 cosine theta. I don't know where that went. So that's our answer. That is how we derive. It's not that big of a deal. It's just solving, but without having to plug in numbers. Honestly, whenever you see a derive an expression, it should get you excited because it means you're not going to be able to make a calculator error. All you have to do is probably some simple algebra. If you're in calculus, it may have maybe some relatively simple calculus, just showing you know when to take a derivative and when to take an integral. Okay, so I've erased all that stuff. Now let's look at, it's impossible for the angle theta to become 90 degrees and both ropes to become horizontal. Using your 3 case diagrams above, explain why. Then explain using your equation. All right, so the 3 case diagram, that was the hanging traffic light situation right here. These are like traffic lights. So engineers have to figure out the angles that they're hanging, or used to figure out, I suppose. Why, as the angle gets lower, why can it not ever reach 90? Well, let's look at it. If we have a free body diagram where it's like this, and it's like this, and it's like this, are we still in equilibrium? No, there is no vertical component here to cancel out gravity. So that means this thing's just going to fall down to the ground. There has to be a vertical component of gravity to balance out the weight. So coming back over here, and then it says, explain why using your equation for F. We said F equals mg over 2 times cosine theta. Well, what's cosine of 90? 0. Are you allowed to divide by 0? No. And this is like the crazy magical thing that physicists get excited about. We now have math to explain what's happening in the real world. We can't ever just bring it down to be exactly horizontal because you have to have a vertical component. That's the physics explanation. But then you bring along this theoretical explanation, this math. If you're dividing by 0, then you're going to have, the force would be infinite. You couldn't have it. So using math laws and logic, we're able to see that 90 degrees is absolutely impossible. And then using physics, we're able to see 90 degrees just doesn't make sense.